have a question because I don't know. How many students are you? And because they didn't give me the information on how many students are following this course. So I didn't ask, and I'm just wondering. Can anybody tell me how many are you? No one. So please, can you say how many students are following this course? How many students are in the master? I don't hear anything. It's a... Muskin, Mahmudov, how you know how many students are in the master? Sorry, I cannot hear anything if they speak. There is a problem. I don't hear anything. Maybe they are speaking, but I don't hear anything. Can you try to tell me something? I don't hear anything. So can you hear me? Wait. Can anybody hear me? Yes or no? Because I don't hear. Okay. Can you hear me? Can you hear me?
Yes, we can.
Yes.
Ah, okay. Even earlier.
Even earlier.
Okay. Because I cannot hear anything. And so, how many students are in this class?
We don't know how many are in the class.
You don't know.
In the diploma, there are 10 students.
10 students, but you can choose.
You can choose, yeah.
Okay, so here I see 6, and then we start. So yesterday probably you were a little bit more, but so shall we start?
Yes.
Yes.
Okay. So I forgot to say about the exam. And the problem is that I don't know yet how to organize the exam because it depends on the situation. I would like to have a written exam because it's the best, in my opinion, for this kind of subject. But we have to adapt. So as soon as the situation is clarified, I will try to. So I have a question for you. For example, anybody of you follow the real analysis course?
Yes. All of us.
All of you. And how many, how was the exam?
Written in the class.
Was what written?
Yes, written in the class, in the good English form.
So if we can manage, we will do a written exam. Otherwise,
we can do in class.
Otherwise, okay, we will do by Zoom. Okay, so let's recall yesterday what we did. So we are still studying this Hahn-Banach theorem. And okay, just to sum up, instead of giving the general theory, let's sum up which are the most useful thing here. And so we have the following most used, let's say, results. So the first one is that if G is contained in E and E is not, okay, here we work in normed space. And F is from G, let's say G, small g is from G to R, such that G x less or equal than a constant times the norm of x. Then there exists F in the dual such that the norm of F is less or equal than M, and F is an extension of G. Okay, so here I'm using the norm as that subadditive function. Now, we have the two separation results. So if A and B, convex, non-empty, is joint, A open, then there exists, okay, an hyperplane, a closed hyperplane, separating A from B, which means F of A is less or equal than, okay, this is open since it is an open map, but okay, alpha, wait, is less or equal than F of B. The writing is not very precise, but okay, you understand. And now the second form is when one is compact, so, and the other is closed. So as usual, it's convex, non-empty, is joint, and closed, and A is compact or B is compact. Okay, then okay. There exists again this closed hyperplane, strictly separating A from B, which means now that for some epsilon, and F of A is less than alpha minus epsilon, alpha plus epsilon, F of B. Okay. These were the two forms, the two geometric forms. Some corollary which is not so interesting. So now we are going to introduce an additional space, which is the B-dual space. This is very important. Okay. If E star is the dual space. So recall, what is the dual space? The dual space is star. Call it the dual space. Is the space of all F linear f from E to R linear continuous. And the norm on E star, so E star is a Banach space, and the norm of F star, okay, sometimes it is clear by the symbol which norm I'm using, no? So F, if I don't put this one, is clearly the dual norm, but okay. Just because maybe I forget. Is the sup, okay, that's of Fx over the unit ball. So it's like the maximal slope. Now, so E star is a Banach space. In particular, it is normal, so I can produce the B-dual space. And this is what? Let's say, so the symbol I use is psi, are the psi, which are from the dual space into R, linear and continuous. And well, I just rephrasing what is written here to the space E star star. So it is a Banach space. And whose norm is the supremum over the linear function whose norm is less or equal than 1. So I'm just copying, and this is psi applied to F. Okay, and here I'm not very coherent because well, it depends on what you use. So in the book, it is used the notation Fx, and this would be psi F. Okay, so the important thing about the B-dual, well, a priori you can go on, no? And however, there is a canonical injection. What is it? It's written the canonical injection. Yes. Okay. So I'm associating from every vector in the original space a vector in the B-dual space. And what is the canonical injection? How it is identified? Defined by. So I have to define psi x, and psi x is defined as a function. So psi x applied to F. And I say that this value, is somebody talking?
The camera is not moving.
Pardon?
The camera.
The camera?
Is not moving.
Oh, yes, you're right. Unfortunately, I don't have the command for the camera. I don't know how to select the camera. Okay. Yes, but you don't see the same. Okay, now it's
okay.
So this real value is defined equal to this real value. Okay? So the map is perfectly defined. Because given x, I define this real value, and I say that this is the value of the linear map. So now let's compute the norm. So what is so let's say psi x, or well, in the book it's written
norm of x from previous corollaries in the last lecture. Norm of psi x equal to norm x.
Yes. Then norm of Well, because of, well, one of the application of Han-Banach, no? So here I'm extending the particular functional which associate to, if you remember, this is the extension of the functional g of x. So let's say x of x is equal to, let's say, tx, for t norm of x, for example. Okay, this is how to obtain that the supremum of the norm is equal to. So we saw last lecture. Okay. So this means that J is linear. It is clearly linear from this guy. Is a linear isometry. Which means that the image of the original set, when embedded into the B-dual space, is a closed subspace. I remember when I was, well, many years ago, a student started thinking how to, well, if you can say anything, but at the end, if you could say anything, somebody would already written it somewhere. So now in definition, very important. If J is surjective, then we say that E is reflexive. Okay? So for reflexive spaces, what happens is that, so in this case, one identifies E star star with E. So for some spaces, well, in general, what happens is that if you start with E, you have E star, then you have a E star star, which is larger than the embedding, so you have more elements, and then you can go on, E star star star, and then you on forever. For reflexive spaces, instead, once you have E star, essentially E star star is equal to E, so you go back. There is no need to add additional spaces. And that's why it's called reflective. You know, it's like you go, then you come back. So the thing is that usually, so reflexive spaces, well, even for non-reflexive space, you don't go over the B-dual space. Because it becomes too much complicated. So, I have a question for you, actually. Did you see the spaces like, so did you see, sorry, or have you seen the spaces L, P?
Yes, it was reflexive if P varies from 1 to infinite. If P doesn't equal to infinite, then LP is reflexive space.
Yeah. But how many of you knows how? Because many exercises are on these spaces. These are like the easiest space where you can see all the structure. So somebody said, yeah, I have already seen, and you know which are reflexive, which are not. And the others?
Yes, we have seen this space in real analysis course.
Okay, real analysis. And you know the reflexivity of the space in real analysis?
Yes. And large LP also reflexive if P does.
Yeah, that doesn't matter. It depends only on the measure space.
Yes.
Okay.
We are just counting measure.
So the exercises are on this space very often. So now we define the orthogonal sets. Orthogonal sets. if M is contained in E is a linear space, linear subspace, then we define the orthogonal space are all the F in the dual such that F of M is equal to 0. So the kernel of F contains M. In a similar way, if N is contained in E star, the orthogonal space, here I'm coming back, are all the X in E such that, okay, F of X is equal to 0 for all X, for all F in N. Okay? So the proposition M orthogonal is equal to the closure of M. While N orthogonal contains the closure of M. Okay, so before going on, I just okay, let's see if you can no, let's do the proof. I wanted to say something, so let's do the proof. So let's start with the first. Okay, first of all, M orthogonal is closed. So first observation, whatever is M, whatever is N, M orthogonal and N orthogonal are closed. Because the closure, so because the convergence in norma is the pointwise convergence, and the pointwise convergence means that it is 0. So now let's compute. So if, let's start with the first, for example. So if X belongs to M orthogonal, this means that F of X is equal to 0 for all F belonging to M orthogonal. But, okay, if you read this guy, it means, okay, okay. And now this is exactly the relation here. So X belongs, so sorry. Well, I mean, I'm so confused. And then, yeah, okay. Okay, and then in particular, it means that, sorry, I mean, if you're confused, it's a stupid thing. So, yes, sorry, I have to prove that if X belongs to M, and F belongs to M orthogonal, then, okay, why I should say that F X equal to 0 implies, and this is exactly means that F X belongs to M orthogonal. Okay, this is the implication. So if this relation holds, implies this relation, and if you look back, is exactly the relation that tells you that X belongs to M orthogonal. Okay. Well, and the same for F. So if F belongs to N and X belongs to N orthogonal, this means I say the same. And so I read as saying that F belongs to N orthogonal. So I deduce the following, that the conclusion. So I deduce M orthogonal contains M, and N orthogonal contains N, and they are closed. Are closed because every time I apply the orthogonal thing, I'll get something closed. So now let's see why here I have the equality. If X does not belong to the closure of M, okay, X0, so I'm going to apply one of the results down there, which tells me that there exists this one. So there exists an F separating X0 from M. By Han-Banach, there exists F0 such that, okay, strictly separating, which means that F0 of M bar is less than some alpha, less than, well, okay, I need just this guy, F0 in X0. But now M bar is a linear space. So the only possibility why its span is not R is that it is 0. And this implies that F0 belongs to the orthogonal of M. But on the other hand, it tells me that X cannot belong. So since the second one, implies that X0 cannot belong to M orthogonal, because there exists an F in M orthogonal such that this relation does not hold. Okay, so you see, okay, in general, however, this thing holds. And it's interesting to understand why here I cannot prove the result. So you have any clue? The clue is the application of Han-Banach. I can still apply Han-Banach to the second situation. But it tells me that you have a functional in the B-dual space. Okay? So the new function, instead of having a function in the dual, I will get a function in the B-dual space separating the closure from a point outside the closure. And then if I look back, well, so this object, so the separating function will be an X for sure if the space is reflexive. Otherwise, well, can be something which is not in the range of the isometry. And so I'm not telling anything. Okay? So this is the reason. Now we proceed, and then we take, so we lead a little bit the general theory, but we start with the theory of conjugate convex functions, which is very important because convex lower semi-continuous function is the bread and butter of functional analysis and calculus of variation. So we can cancel. And we remember that there are these two geometrical things. So the next step is conjugate convex functions. roughly speaking, what I want to study the Lejeune transform. Or let's say phi star of f is the supremum over x of f x minus phi x. So this is the conjugate function given a convex function phi. So phi will be convex, lower semi-continuous, and I'm going to study phi star and obtain some good relations because they play, this duality plays, well, well, when you have to work with convex function, it plays a lot of things like for Fourier transform with L2 functions. There are many similarities. Okay. So the assumption on phi. So phi is lower semi-continuous. Okay, lower semi-continuous means that phi to the minus 1 of minus infinity a is closed. And phi is convex. Okay, phi, for us, it maps E into minus infinity plus infinity. I'm allowing even the value plus infinity. So there is no ambiguity when I just add functions because I will never get 0 plus infinity. Minus infinity plus infinity. Phi convex, which means that phi 1 minus t, ty, 1 minus t, t phi y. And t is in 0, 1. And okay, since I never get minus infinity plus infinity because of the assumption. So another object, okay, let's make a drawing, and then we introduce the thing, the objects. E R, and then I have the graph of this function, which is okay, convex and lower semi-continuous, so maybe it's like something like this. And here I can go to plus infinity. Okay, and here, okay, it doesn't matter. So this object here is the epigraph. So AP, a function phi, well, in general, are the couple x lambda such that lambda greater or equal than phi of x. Now let's see the relation. So if phi is lower semi-continuous, then well, the relation is the same. The epigraph is closed. Phi convex, then the epigraph of phi is convex. Okay, the lower semi-continuity means, even for a general function, that if xn and lambda converges, because of lower semi-continuity, the limit here will be below of the limit of the lambda. So it is closed. And the convexity, well, I just take the object here. So if this is less than lambda, this is less than lambda prime, then I'm saying that the value is less or equal to the linear combination of lambda, lambda prime. So these are very easy statements. And another observation is that phi is convex. Phi less or equal than t is convex, but only with this implication, not the other one, no? So other interesting thing is that phi convex or lower semi-continuous, one of the two, then the supremum, so any family, even uncountable, is convex or lower semi-continuous. And even the sum, okay, these are very simple things. So now the domain of phi are the x such that phi of x is less than infinity. Okay, so we have this nice class of function with some properties. At least I can describe the function, even looking at the function or looking at the epigraph. And actually, it's the same. It's still the same, but the epigraph suggests something, no? Because this is a convex closed set. Okay? So it's nice, it's useful because I can apply one of the geometric form of Han-Banach. And the geometric form of Han-Banach will let me study this object here, or the whole difference, because this will be represented as the value of a linear function over the product. Okay. So let's go on. Definition. The conjugate function. So the definition is the one that I gave there. So it's phi star, which maps from the dual space into, okay, a priori, I don't know, I have to verify, but let's say it's from minus infinity to plus infinity, defined by phi star of x is equal to the of f supremum over x, and this is fx minus phi x. Okay. Now, if you look, what does it mean, this object here? Let's go back to the graph. So the f means it's a linear function. So I'm saying, so this object here, for fixed f, is a linear function minus the graph. Am I taking the supremum, or I'm taking the infimum of phi minus f of x? So let's say if this guy is, okay, let me draw in the red, is fx, so the linear functional. So what I'm looking there is the supremum of the difference. So it's, I'm looking at the point, which can be maybe this one. Where I cannot go further, because, so the value, this value here is the phi star at f. Okay, so the drawing is clear what I'm computing. Now, the thing is the following, is that if the domain of phi is not empty, well, clearly, if the domain is plus infinity is completely trivial, then I have for sure that phi star is different than minus infinity. Okay, so at least I'm not assuming minus infinity. Now what I want to prove is that actually so what I want to prove is that actually even domain phi. So this could be plus infinity everywhere. So let's say this is not the case. So some observation again. So phi star is lower semi-continuous convex. And from the thing before is that the domain of phi star, sorry, and well, this is different from plus infinity, from minus infinity. So I'm still in the class apart to say that the domain is not zero, is not empty. Okay, so why it is so? Because phi star is the supremum of linear functions because for any f, the linear function is f maps to fx minus phi of x. Okay? So I'm taking the supremum with respect to x of this family of functions, which are convex and lower semi-continuous. That's it. So this part is very easy. Another easy observation from the definition is that I get the Young inequality in some sense. Okay, from this guy, phi star of f is greater or equal than fx minus phi of x for all x and f, by definition. And observe that it's perfectly meaningful since I never have minus infinity. So I can write fx is less or equal than phi x phi star of f. Okay, and well, if you do the computation for some norms and then you're able to compute the dual, yes, you get exactly the Young inequality. Okay, proposition now, the important proposition. Phi is, okay, it's proper, which means domain of phi is different, than the empty set. Lower semi-continuous. Convex, I think, is not needed, but okay. Then phi star is proper. So the domain is not the domain of phi. Sorry, there exists f phi star of f is less than plus infinity, lower semi-continuous, and proper. Okay, so the Legendre transform maps the nice set of convex functions, which are the functions which are lower semi-continuous convex and the domain non-empty, to the same set. Well, in the dual space, but the set is the same. So essentially, I can compute the dual, the pre-dual, as I did for the orthogonal. So for example, with this thing, I can write that phi star star is equal to the supremum evaluated in x is the supremum over fx minus phi star of f. So I can go back and forth. And I'm not going to stop. Okay, let's do now the proof. So the only thing it was not elementary from the definition is that the domain is non-empty. If I have space here, let me see if, no, unfortunately, no, it's non-trivial, the thing. So I need to get some space somewhere. And let's erase here and keep the picture. Chocks is something quite okay, so let's take our statement and let's consider which property I have from the assumption on phi. So the epigraph is convex, closed, and non-empty. Okay? So this thing means that the epigraph is non-empty. So there exists one point, and here let's make, there exists some x. So let me cancel now all these objects. Then I have for this x some value, which is phi of x. And, well, the epigraph contains at least this line can be larger. No? Naturally, the epigraph can be something larger. But certainly, I have a point x and a value. Moreover, I take another point which is not in the epigraph. For example, this point here, this is the point x, and that's lambda not belonging to the epigraph. So I have the 2 points, well, a closed set and a compact set which are disjoint. So there exists, say, x0 and lambda 0, just to distinguish, not belonging to the epigraph. So now we apply Banach theorem to the product space for these two sets. The set with sets, let's say, AP phi and x0 lambda 0. So the result is that there exists a function in the dual of this space. Okay, function in the dual of this space is easily seen. The couple, a function in this space, and well, it's a constant in the other space, which is the product. So there exists f and alpha belonging to E star times R, which is identified to E times R star by the trivial identification, such that I have a strict separation, no? So let me say that f, okay, let me see the sign. Okay, in this way. This is f0 and alpha 0, just to remember. f0, x0 plus alpha 0, lambda 0 is less than, okay, some value beta, less than f0 x plus alpha 0 phi, well, should be lambda for all lambda greater or equal than phi of x. So which is the minimum will be phi of x here, of course. So the key point now is that I need to conclude that okay, so now the key point is that this alpha 0 cannot be 0. And so the drawing is the following. If alpha 0 is 0, then the plane, so I just have this plane, with this hyperplane, which is f x plus alpha lambda equal to beta, which separates both sets. But if alpha is equal to 0, you will get this plane, which is not strictly separating it. So it's a little bit subtle. Otherwise, let's assume if I write this for x equal to x0, I get f of x0 plus alpha 0 lambda 0 f of x0 plus alpha 0 lambda okay. So from here I get alpha 0. I wrote some with a minus probably. There is some. No, okay. It's alpha 0, lambda 0. And this is a contradiction because if alpha 0 is equal to 0, they are equal. Okay? So the strict separation is important. Okay. Once I have that alpha 0 is different from 0, then what I can get from this observation, then beta is less than f0 of x plus alpha 0 phi of x for all x divided by alpha. So I get that phi of x plus f0 divided by alpha 0 applied to x is less than beta. Sorry, is greater than beta. So I need to reverse the thing. So it's minus thing plus minus this guy is less or equal than less than minus beta. I need to reverse because I want to have in the form of so in this form, no, in the dual form. So this means that phi star computed in minus f0 divided by alpha 0 is the supremum over x of minus f0 alpha 0 x minus phi of x. And from this observation, this guy here is less or equal than minus beta. So the conclusion is that the domain, this point belongs to the domain of phi star. So it is proper. Very well. So now we have that the Legendre transform is a nice operation. Now the second observation is, what about phi star star? Is phi star star equal to phi? So it is natural, no? When I wrote this this way. And the remark, so let me go here. Here I can cancel. Okay, so let's so let's put further statement. Theorem is phi is proper, the only standard assumption, lower semi-continuous convex. Then phi star star is equal to phi. So you start seeing the similarities with other functional transforms. No, they are well, they are when applied twice, you get the function. You recover the identity. Okay, the remark here. So this proof is very close to the proof that M orthogonal is equal to M. I leave you, if you want to try the exercise, because you take phi is the indicator function. So and this function will be denoted from now on like the indicator function of phi x of M. You do the computation, and then you discover that what you're exactly computing are the orthogonal spaces. Okay, so let's do the proof. Okay, assume first, just for simplicity, phi greater or equal than 0. Okay, I don't know if, well, maybe we'll discuss, but in any case, the thing is that since phi is proper and lower semi-continuous, I already know that there is a plane which remains below to the epigraph, so for a general phi, you take phi plus a linear functional. Say, in one point. Or minus, well, depends, plus some constant. Which is essentially, I'm adding this affine function to the epigraph, and I'm bringing up the epigraph to the positive set. So this will be the last part. So that's why you can always assume that. So now, first observation. Let's go back to the Young inequality. Young-like inequality. Okay? So what I deduce that for all f, in particular, if I take the supremum, so the supremum with respect to f of this function is phi star star. Okay? So and now the second part is, again, the Hahn-Banach theorem. So the drawing is very nice here, because is the same. Assume by contradiction that there exists x0 such that phi of star star of x0 is less than phi of x0. Okay, so the drawing is the same. I have this point, which is x0, and I have some value here, which is phi star star of x0. Now we see what we are going to do. We are going to take the same separating hyperplane, separating strictly, so the hyperplane will be essentially of this form, and then we get that the value phi star star will be higher than phi star star of x0, which is a contradiction. Okay? So again, so we repeat the proof. So apply Hahn-Banach to the sets. So the epigraph of phi and x0, phi star star of x0. So we get the alpha 0 belonging to E star times R, well, that is the same, such that well, the relation is the same. F0, x0 plus alpha 0, instead of having a point, now I have my value, which is phi star star of x0, less than beta, less than f of x, plus alpha 0, phi of x. Okay? As before, since the separation is strict, alpha 0, well, here I use something more. Alpha 0 it should be positive. And I forgot to say in this proof here that since I'm divided by alpha 0 is positive. No? So because this is for any lambda, so this guy is larger than this guy, so it cannot be negative. So alpha 0 is, then I get, well, if it's 0, and then alpha 0 should be greater than 0. I forgot to say even here, otherwise I cannot divide. Okay? So now what I get that no, wait a minute. Here it is not. I'm getting confused because it can be plus infinity, this guy. So I get only this guy here. Yes, was the opposite. Because phi of x can be plus infinity, no? While before was not plus infinity. So that's the main difference. So this can be larger or equal than 0, doesn't matter. Okay, from this observation, then I get, in particular, for all epsilon greater than 0, okay, this holds for alpha 0, but this guy is positive, and here enters this assumption. Then I get also beta is less than f of x plus alpha 0 plus epsilon phi of x. And now this guy is greater than 0. Okay, so now rearrange the terms, and this gets that phi of x, or let's say minus phi of x, plus minus f0, this should be my f0, divided by alpha 0 plus epsilon applied to x is less than minus beta. And so I read beta divided by alpha 0 plus epsilon. And this reads as phi star evaluated in this point okay. Which is the same proof as before, more or less, but here I get it. I'm using this value. So now compute in x. Okay, this is greater or equal than the value computed in this particular function. So it is. So okay, let me write better. This is the supremum over f okay, which is greater or equal than the value. So the value of this linear function computed with this particular slope. But now I know that this guy, okay, or minus this guy, is larger than beta over epsilon, no? So okay, so now let's rearrange terms, and so I get that, so I multiply by alpha plus epsilon, so it is f0x. This guy multiplies this guy. And what I'm left is this guy. Okay, this holds for all beta, for all epsilon. But this is a contradiction with respect to my separation assumption, contradicting f0, okay, x0. So this is evaluated in x0, doesn't matter, plus alpha 0 plus epsilon phi star star x0, without the epsilon, is less than beta. So the important is the strict less also in this analysis. So conclusion, the proof is, well, there are some computation, but you see the idea is easy. So once I separate one point from a set, I'm using this slope. And well, in either I can, well, I need to recover from this slope a linear function over E, which will play the role of the function with which I estimate the supremum over here. Okay, I need to choose one particular one which will allow me to prove that the inequality I'm looking is right or is wrong, whatever I need. So the idea is the same. So now, I don't know if you want me to do the general case. The general case, you see, I just subtract. Let's just make, as an exercise, what happens when I subtract a constant and a linear function, just to see. So as a final, as a remark. That is, I just write in this very border part of the blackboard. Or the remark. What is the Lejeune transform of I add a linear function and then I add a constant? Okay, this is the supremum. But this is, okay, f x minus the function And you see the C is exiting. This guy is collecting into this guy. And is equal to, well, the translation, phi star f minus f bar minus C. Which, if we go back, and is the same, if you remember my original interpretation that you have a line and you want to see what is this difference, well, if I change the slope because I'm subtracting an affine function, well, you see that, sorry, this should pass to the origin. You see that what happened is that, well, the constant plays out because if I'm lowering it or increasing, it appears with the other sign. And the slope, what happened is that it's subtracted or added, which is the formula. So with this formula down there, you solve even for the general case. And we are not going to do that. Now, I want to conclude this part on the Hahn-Banach with an important duality result. What I can say, for you will be something that it's some technical application, but I tell you that this appears in many different subjects and it is very, very useful. So, so it is a minimax result, which means that a min-max result, so I'm transforming a minimum problem into a maximum problem. And so let's cancel this. And we will use the whole blackboard. I don't know if I can finish by today because it's quite long, unfortunately. But it is very useful. Okay, very quick. Are there questions on this part? I know that seems a little bit technical, maybe, but it's not. And the last result, well, is very useful, but is not needed in the future of the course. But I think I discover by myself how it is useful when I have to solve some real problem. Are there questions so far? It's very difficult to interact with an empty blackboard.
No questions.
Yep. No questions.
Yes.
Okay. So, you know that in Italian and in English, the use of yes or no is slightly different. Now, when you say no question, yes, it means you have a question. Or another language, no question, yes, it means you don't have a question. So it means you don't have a question.
Yeah.
So, okay, let me state the theorem, and I'm thinking maybe for today it's better to do some exercise, just to see some exercise on the subject. Then we have a tutoring, but otherwise it will be something too much far away. So let's state the theorem. So it's phi, psi are convex, lower semi-continuous. And now the subtle assumption is the following, and there exists x0, which belongs to the domain of phi intersection the domain of psi, such that one of the two, and here I don't remember which one I choose, phi. In x0. Then the infimum over the original space of phi of x plus psi of x is equal to the max in the dual space minus phi star of minus f minus psi star of f. And the existence of the maximum is part of the statement. Okay. And we will do some exercise I don't have time to address because the proof will be split into parts. But I want just to notice, in your opinion, why I need some continuity. So if you think to the Banach and Banach theorem, so the continuity of phi, what does in x0, what does it imply in the epigraph? Okay, well, it implies essentially that you know that above here you have a ball. Okay, and this is the way that you will use Hahn-Banach theorem. Well, one set will be open. Or actually, when it says that, on the other hand, it says that this plane cannot be vertical. Okay, so we do next time. It takes a little bit too long. So let's see some easy exercise. Quality. Because some I want to give to the okay. So in the textbooks is the exercise 1.3. So now the space, the Banach space is equal to C. So it's U is continuous from 0, 1 in R, and U of 0 is equal to 0 with the usual norm. So the norm of U is the max. And the function I want, f of U, is the integral from 0 to 1 ut dt. Okay? So, I want to, the question is, show that, so whether there exists U bar such that f U bar is equal to norm of f. Okay, let's work about norm of f. So norm of f is the supremum over U of the integral ut dt. So this means that U is less or equal than 1, so certainly this is less or equal than 1. because the norm less or equal than 1 tells me that the maximum of this value is 1. On the other hand, if I take u is equal to, well, just draw the function, let's say is nx for x 0, 1 over n, and 1 for x greater than 1 over n. So the integral of un, okay, I may compute is n 1 over 2n plus 1 minus 1 over n. So it's 1 minus 1 over 2n. So this tends to 1, which means that the norm of f is equal to 1. Now, it is clear that there cannot be any u which satisfies this relation. If u such that the integral from 0 to u dt is equal to 1 and u less or equal than 1, then u should coincide with 1 if u is continuous. And so u does not belong to E. And now I have a question for you. So is E reflexive? Okay, this is for you. Let me see another exercise. This is it's okay for the tutorial. Long. Okay, let's see another. Something which is short, not too long. Okay, let's do this guy on the reflexive. So we take E is L small 1. So we know that E star is L infinity. So it's not. Now N is C0. So these are the sequences Xn which converge to 0 as n tends to plus infinity. No? So it is contained in L infinity. Now, what is n orthogonal? N orthogonal are all the function f in L1 such that f, on the function, or let's say, or the point x in L1 such that f x is equal to 0 for all f which is in C0. Let me change chalk. Okay, this is the definition. But now C0 can be any sequence, no? Just the limit is 0. So in particular, taking, let's say, Fi equal to 0, 0, 1 in the position I, 0. Turns out that so the dual product here, which I didn't say, is the sum.
And 0 in orthogonal, just 0 vector.
Pardon?
0 vector in orthogonal. Origin in orthogonal.
In
orthogonal equal to 0 vector, just.
Equal to 0.
Vector. No.
For all f in C0. Yeah, what's the problem? So
No,
n is C0, so I'm looking n as a dual of L1. So it's the product, it's correct.
If n orthogonal equal to 0 origin in L1, just.
So well, this is the sum, let's say Fi xi, which is equal to xi of this particular, let's say, I bar. And so I say that n orthogonal is equal to 0, which is not surprising since I know that the dual of C0 is equal to L1. So essentially, I'm using the following hierarchy. C0 is L1, which is the dual of C0. L infinity, which is the dual of L1. So it's C0 star star, and then the canonical map, the canonical injection is, well, it's C0. Okay? So essentially, I'm saying that, okay, so conclusion of this exercise, what is now n orthogonal? Is L infinity. Because n orthogonal is 0, so every f value of 10 is 0 is 0. So conclusion, this is an example where we have that n orthogonal contains n. And is exactly the easiest example, which is the canonical injection. Okay, so I have still to arrange with well, I give the exercises that I think are useful. You can try to do all the exercises. When I was studying, I did all the whole exercise. At that time, there was no exercise. It was written at the side of the text that you can prove this, see exercise, you prove this, so you reconstruct the theorem. But okay, here there are a lot of exercises, and so we have seen some. So next lecture, which will be Thursday, we will finish this theorem, and we will start with the uniform boundedness principle and the bare category. I think you have already done bare category theorem, no?
Yes.
Okay. So we will review it. Well, the proof is short, but not uniform boundedness and so on. No? Open mapping, closed graph, uniform boundedness, you didn't do that.
We have studied, yes, uniform, just Banach-Stenghaus theory, uniform boundedness.
You did already?
Yes.
But we don't did it in the previous semester.
You did in the previous semester.
We didn't.
Pardon? Pardon?
We don't.
Ah, no, not all then.
Yeah.
Okay, so I will repeat them. Okay, so if there are no questions, see you on Thursday. You can, wait a minute. For whatever thing, you can write to my email. Because it's difficult to communicate, so my email, and then we can arrange an online meeting. Okay, so it's my surname without the final I, and well, the domain is CISA. That's it.